Okay, so a couple of things of note. Okay, first thing is that your Unit 4 exam, that unit that we kind of started the other day. Okay, the unit exam for that unit is going to be June 14th. Okay, I've got to set a day for it because I've got to know how many days I have to finish. Okay, that gives us basically then we might get 1 day for review before that if we're done a little bit early. If we're not, then we'll have a chance to go over that unit exam on the 15th, which is the last day of classes. Okay, and maybe do some final exam review if we're lucky. Okay? Right now, it doesn't look like we're going to have time for final exam review in class. Okay? I'm going to try and go faster if I can, but I want to make sure we understand the stuff in this unit. Okay, that's more important. All right, so that's kind of where we're headed here going forward. Now, for the simple harmonic motion stuff we talked about the other day, we talked about two types of simple harmonic oscillators. The mass on a spring, okay, and we said that the period of a mass on a spring can be calculated using this formula. The two things that could affect how long it takes a mass on a spring to oscillate back and forth one time are dependent on the mass that is attached to the spring and the stiffness of the spring itself, M and K. Right? We also talked about a pendulum. Okay, and for a pendulum, the period of a pendulum was dependent on the length of the pendulum and the acceleration due to gravity, not the mass. Okay, because all things fall at the same rate. So those formulas are on your formula sheet. Okay, but that's what we were looking at yesterday, or not yesterday, the day before yesterday. Okay, so I'm going to have you do a few practice problems using those formulas. And then we're going to move on to Hooke's law and conservation of energy in simple harmonic motion. Okay, like honestly, the simple harmonic motion part of this unit is going to take us about 4 days to move on. Okay, and then we're going to move on to waves, okay, because well, we don't really have that much time left. Okay. All right, so from your digital workbook, I would like you guys to do questions. Four. I'm going to write them up here, guys. Hang on. 4. 7. 10. 12, 13, and 14. Okay, so you got 3 mass on a spring problems. Although one of them isn't, it's about a mass on a spring, but it actually doesn't require you to use the formula. Okay, and then you've got 3 pendulum questions. One other thing that's going to come up. The relationship between period and frequency. Okay, remember that period is 1 over frequency and vice versa. Because on a lot of these questions, they don't give you the period. They give you the frequency instead. Okay, and so you're going to have to get the period and then go. Or you're going to calculate the period and the question is going to ask for frequency and you're going to have to find the frequency instead. It's just one extra calculation using that formula, okay, but it is something that you'll have to do, okay, and be aware of. Units for period are generally seconds. Units for frequency are generally hertz. Yeah, Hz, which is cycles per second. And for period, it's seconds per cycle. Okay, so they're the inverse of each other. All right, I'll put those questions back up on the board. Okay? And you can get going on those. Maybe I can even make it a little bit bigger. And now it won't let me move it. Okay, there we go. Okay, so what we're going to look at here is stuff to do with restoring force, okay, specifically to springs. Right? If you recall from the first lesson, the restoring force is the force that is bringing the object back to equilibrium. Right? In a mass on a spring, that's the spring force. Okay? In a pendulum, it's the component of gravity acting along the arc the pendulum is following. Right? But for most part here, we're going to look at the restoring force being in a spring. That's what, after all, Hooke's law is all about. Okay? So we need to understand the relationship between restoring force, F, which will be in newtons, okay, spring constant, K, and displacement, which in this unit is going to be denoted with an X instead of a D with an arrow over the top. Okay, and the reason for that is because it's measured from equilibrium, not from final position, initial position, etc. So it's a slightly different notation. Displacement will be X in this unit. Okay, we also need to understand that energy is conserved in simple harmonic motion, okay, and that potential energy in simple harmonic motion for a mass on a spring, okay, is elastic potential rather than gravitational. For a pendulum, it's still gravitational. Right? But for a mass on a spring, we're now talking about loading a spring by doing work and then allowing the spring to release that energy and convert it back and forth between potential and kinetic. Okay, so I don't know if you guys remember Hooke, okay? Not the captain, the scientist. Okay? He's the guy who invented the microscope. The first person to view cells. Right? Because he was a physicist, not a biologist. Okay? And he was doing experiments with lens systems. He's like, if I put two lenses together and I find their focal length, which is where they concentrate the light, okay, and I put the lenses in these positions, I can alter the path of the light such that I can diverge the rays. And he found out that he was right, and that by diverging the rays, he could make things look bigger. And then he's like, all right, biology could probably use that. Here you go. Back to real science, physics. Okay? And so then he went back and he started looking at springs and restoring force and energy. Pretty simple experiment. He hung a spring from the ceiling and then hung various masses from it. Okay, now what force is pulling on those masses? Gravity. Now as long as the mass isn't accelerating, that is, isn't oscillating up and down, then that means that the net force is what? Zero. Because it's just hanging there. So that means that the gravitational force downwards and the restoring force in the spring are the same. They're equal but opposite, right? The restoring force in the spring is trying to pull the spring back up. Gravity is pulling the mass down and the thing just hangs there, right? So it was how he was able to calculate what the restoring force was by just using a force that he was familiar with and that he could easily get, okay? So what he found is if you just hang a spring there, it hangs to a certain length. That's the unstrained length of the spring. We would define that as the equilibrium position of that spring. Then he puts on a certain amount of mass and records how much longer the spring is now, okay, or how far from that equilibrium position it's stretched. So he probably just hung it next to a wall, marked it on the wall, and then put a mass on it, marked it on the wall again, and then hung twice as much mass. Well, when he hung twice as much mass on there, how much further do you suppose it stretched the spring? Twice as far. Okay? So he found that there's a linear relationship between the displacement and the amount of restoring force that's present in a spring. And this is true for all simple harmonic motion. In fact, on the first day we learned that that's necessary for simple harmonic motion to occur, that the restoring force must vary linearly with displacement. Now, all springs have a truly elastic region. Okay, and that is the area, the different lengths they can be compressed or stretched to where that would be true, where that restoring force would be linear with displacement. If you pull a spring too far, what happens to it?
It'll break.
Generally before it breaks, it'll do something else. Yeah, well, it stretches, but if I don't stretch it too far, it'll go back.
Oh.
If I stretch it too far, I'll deform it permanently. Okay, you've all seen that, with the pen springs, right? You do this and it's like, oh, well, that's great, now it's not gonna work anymore. Okay, so there's sort of a narrow elastic range for any spring. Okay, it has to do with the spring constant, it has to do with the length of the spring. But know that there's a point where if you stretch a spring too far, it's not going to go back. Hooke's law breaks down after that point. Okay, and the same is true for compression. You can damage a spring by compressing it too far. Okay, you'll get to bend in the middle and then deform. Okay, like all of our slinkies, they all look like that. Okay, they've all been twisted and deformed and so, yeah. All right, so does that idea make sense? So this is what Hooke discovered. The force in the spring, which was equal to gravity, is equal to negative K, the spring constant, the stiffness of the spring, times the displacement, x. What do you suppose the negative sign is in there for? Is force a vector quantity?
Yeah.
Okay. If I take a spring and I stretch it to the left, which way does the spring pull?
The opposite way.
The opposite way. The negative sign is there to make sure that the force is always opposite the,
Force?
okay, sort of, or displacement,
Yeah.
right? If I displace a spring to the left, I need to get a force in the spring that is opposite that. Okay, the spring has to pull the other way if it's going to be a restoring force. I took it and went left of equilibrium. The spring wants to pull back to equilibrium, so the spring has to pull right. Okay, so the negative sign is there to make sure that x and f are always going to have opposite directions. Okay, they have to, otherwise it's going to be helping go the other way. All right, so that was Hooke's law. Okay, there's a certain amount of force. There's 2 times that force. It stretches 2 times as far. Okay, pretty straightforward, right? Okay. So that's basically saying the same thing. The negative sign is used to ensure that the force is always directed in the opposite direction of the displacement. Okay, so if I was to compress the spring, like you see in C here, okay, if I was to push the spring inwards, okay, then the spring has to push back in the other direction, okay? Always going to be, F is always going to be opposite. Okay, now I want you to think back to Science 10 when you did the little rubber band lab, okay, with the spring scales and you had rubber band between the desks, okay? In that lab, you built a graph, and that graph was of distance and force. Okay? And in that lab, distance was the manipulated variable. You picked a few distances and then you stretched the spring to those distances and you recorded the force. And you found what Hooke's law says is true. That the farther you pull the rubber band, the harder you have to pull. And it's a linear relationship. Okay? Is that ringing a bell? Okay. In that lab, you were asked to calculate the work done in stretching the rubber band. Everybody with me there? Okay, so that whole lab was on work. It wasn't anything to do with Hooke's law. We just used Hooke's law because it's perfect. Okay, so in this lab, you had to calculate the work done. In order to do that, you found the area underneath the line on the graph. Okay, how do you find the area of that shape? Right, 1/2 base times height, or base times height over 2. Everybody okay with that idea? Okay, so 1/2 base times height. Okay, what's on the base? Distance. In Hooke's law, that's symbolized with what? X. Okay, so, and here is force. In Hooke's law, it says that force is K times X. It's actually negative, but we're going to ignore that for right now. Okay, it says it's K times X, yes? All right, so when I do 1/2 base times height, I'm going 1/2 X times K times X. Would you agree? Okay. That gives me this formula. 1/2 kx squared. Now, if we look at that in terms of the units we get, okay, K is in newtons per meter, and I'm multiplying that by meters squared. When I do this calculation, this meters will cancel that meters. What's a newton meter? A joule. So when I calculated the area under that graph in grade 10, I calculated the work that I did in stretching the rubber band. What kind of energy did I put in the rubber band? Elastic potential energy. This calculates elastic potential energy. It's the work you do in stretching any elastic object. 1/2 times the spring constant times x squared, the displacement of the object squared. Okay, so that's where that formula comes from. It is equal to the work you do in stretching an elastic object.
Why do you have x twice? Where do you get
Because x is d, right?
Right.
It's force times distance, right? It's base. The
Right.
base is x, right?
Yeah.
Times kx, of course. So I have x in there twice. That's why it's kx squared, right? X times x is x squared. Okay, everybody all right with that? Okay, so that's where that formula comes from. I'm never going to ask you to derive that formula. That formula is on your formula sheet. I just want you to understand where it comes from in terms of work energy theorem. We talked about that in unit 2. Okay, and how it's going to be important in conservation of energy. If I compress a spring or stretch a spring, then I've done work. Agreed? Once I let that spring go, it's going to oscillate back and forth, theoretically, forever. Well, all it's doing then is converting the energy I gave it from that work from potential to kinetic, and so on, back and forth forever. Okay? Will the energy be conserved? Just like a pendulum converts gravitational potential energy back and forth, a mass on a spring converts elastic potential energy to kinetic, back and forth. Okay? So the law of conservation of energy still applies. It's just instead of gravitational, now it's elastic. Okay? But it still sets up the same way it did, okay, for us back in the other unit. All right, so this is what I just explained to you here, where that formula comes from. Okay, and it will apply to this. Okay, back in unit 2, we did the roller coaster questions. You did those back in science 10 as well. Okay, where we said, m times g times h initial plus 1/2 mv initial squared equals mg h final plus 1/2 mv final squared. Okay, that's how a pendulum would work. A roller coaster, a pendulum, a kid going down a frictionless hill on a sled, okay, whatever. Okay, that's the law of conservation of energy when gravitational potential energy is involved. Okay, the formula is basically the same when you're looking at elastic potential energy. Our mechanical energy is still conserved, initial equals final. All that changes is now is we substitute elastic potential energy for gravitational potential energy. Back when we used to have the IB program, okay, here for physics, we would actually get into situations where an object could have all three. Okay? It could have gravitational potential energy, elastic potential energy, and kinetic energy. Okay? And it really doesn't make it any harder. You just have that on that side as well, and you have that on the other side as well too. We don't have to do that in regular physics 20, so that saves us a bit of bother, okay, in not having to worry about that. Okay, So, is doing law of conservation of energy gonna be a lot different than it was before? Not really. Okay, and what can you do with all those halves? You can cancel amounts in every term, okay? Can you cancel mass this time? No, mass isn't in every term. You can cancel the halves, but you gotta keep the mass this time, it's not in every term. All right, how are we feeling about that stuff? Okay, that's what we're gonna go over tomorrow. Tomorrow is Wednesday, but Thursday, we might have a quiz on simple harmonic motion stuff on T equals 2 pi root m over k, that kind of stuff. Probably won't do energy unless we get really far tomorrow, which we could. Okay? All right, we'll leave it there for today.